Hello and welcome to this lecture titled Building Energy Simulation, Model Development, Results Representation, and Analysis. Within this lecture, I will provide you an introduction to model development and simulation results, answering to the following question: how to build valid and credible simulation model, how to use the simulation results, and how to represent them in a comprehensible way. Finally, to conclude, I will provide you some key takeaway to frame the topic. So let's start defining how to build your model correctly since the beginning. Independently by the phase of the design process, the geometry of your building is the first piece of information required to process an accurate simulation. As such, it's very important that geometry you are feeding into the software is set up properly for analysis. When it comes to building performance simulation, there is a common misconception that the more detailed the building, the more accurate the results. Not necessarily true. From an architectural perspective, models are typically outfitted with every detail of the building's design, with the goal of producing realistic orthographic and renderings. There are some details in your building that will have little or no impact on the energy performance, and in fact, they will increase runtime and they can be significant sources of error. It's best, therefore, to leave them out. Keep it simple. An energy model only needs a few pieces of key geometry to represent the building's performance. Once the exterior shell, internal surfaces, and shading elements are properly built, the model is quite ready to be analyzed. For example, at the early design phase, forget furniture or detailed information about people, lights, etc. From the standpoint of getting valuable results quickly that guide your early design decision, there is really no need to spend hours on adding details to your energy model. It's demonstrated in literature that the level of detail in the model can dynamically adapted according to the state of planning. So at this point, it comes up naturally this question: how to build valid and credible simulation model? A simulation model of a complex system can only be an approximation to the actual system. A model is supposed to be an abstraction and simplification of reality, a sort of surrogate for experimentation with the actual system, existing or proposed, which is usually disruptive, not cost-effective, or simply impossible. Thus, if the model is not a close approximation to the actual system, any conclusion derived from the model are likely to be erroneous. The more time that is spent on model development, the more valid the model should be in general. However, the most valid model is not necessarily the most cost-effective. For example, increasing the validity of the model beyond a certain level may be quite expensive, since extensive data collection may be required, but might not lead to significantly better insight or decision. At this point, I like to cite a famous quote by Professor Box, which stated that all models are wrong, but some models are useful. Let's see in detail which are the definitions of validation and credibility. Validation is the process of determining whether a simulation model is an accurate representation of the system for the objectives of the study. That's why a simulation model should always be developed for a particular set of objectives. In fact, A model that is valid for one objective may not be for another. A valid model can be used to make decisions similar to those that would be made if it were feasible and cost-effective to experiment with the system itself. Beside validation, there is the need for the simulation model and its results to have credibility, and this happens if the decision maker and other key project personnel accept them as correct. A credible model is not necessarily valid, and vice versa. The following things may help establish credibility for a model: the demonstration that the model has been validated and verified, the decision maker's ownership of and involvement with model assumption and project, and a compelling animation and representation of the results. Now that we have understood how to set up a credible building model and how to validate it, now let's see how to use the results and how to make them comprehensible. This could be considered the turning point within the simulation process because we are going to take the data and turn them into decision. Data, information, decision, and advantage. These four words are the core of the results analysis and comprehension. In order to take simulation analysis from data to advantage, you need to understand the basic building science behind your building performance. Once you do, you will be able to achieve high performance consistently across your building project. Simulation gives you data. Using your building science knowledge, you take the data and turn it into information. From there, you make a decision to gain an advantage. This advantage will give you consistency and confidence in performing building simulation analysis and to present your results. One of the most important skills of a modeler is to be able to combine problem-solving and visualization skills in order to communicate design ideas verbally and visually, for example, to your client or company. Let's try to understand together how can you incorporate the building performance analysis into your presentation and make building modeling results comprehensible to different target group. In the following slide, I will show you some example of results representation of an overall building renovation at different stage of the process. At the early design phase, it will be very important to represent the key parameters results in relationship to the energy target. In the example of this slide, annual CO2 production and annual energy consumption were chosen as key parameters in relation to the simulation goal of reducing the building carbon footprint. In the first case, the indicator chosen to conduct the performance-based design is the depth of the existing sheathing system, while in the second case, a more important change has been evaluated, considering a new configuration of the building geometry. In those two examples, two different building variables have been evaluated in terms of simulation assessment, but at the end, they will be presented by the same graphical representation according to the simulation objective, reducing CO2 and energy consumption. In this slide, I would like to show you a general example which could be useful to show how responsive each renovation strategy could be in comparison with the others and how they may affect on the overall consumption of the building. My suggestion here is to make always a clear representation of your results in comparison to the boundary condition, giving evidence to the necessary variables to reach the objective of the renovation, and never forget to declare clearly legend, units, And in case of a comparison of different options or strategies, like in this case, to highlight your final choice. Waterfall chart is the last example. It shows the improvements that individual strategies make to the baseline design, with the final bar showing their combined effect on it. With this graph, you can provide clearly the condition and values from the current state through the application of each single renovation strategies until the final configuration. Even in this case, you have to keep in mind the importance to focus only on the key important indicators that could be understood by your interlocutor, building owner or professor in case you are a student presenting your assignment. When you perform a simulation, you usually have a huge amount of results, but as stated at the beginning of this lecture, the model must be developed for a particular set of objectives, and only the parameters important to those objectives must be presented. In this case, for example, I've chosen to show only the heating and cooling results. We are at the end, and first of all, I would like to thank you for your attention and to leave you some key takeaway regarding the topic presented in this lecture. First of all, about the data. Keep in mind that data are not representative of what one really wants to model. Data are not always ready to use. They may be not in the appropriate type or format. Data may contain measuring, recording, or rounded errors, and also data may be biased for different reasons, so it's always important to verify the source. Regarding the model validation and representation, we have underlined that all models need to be validated or we may occur in errors within the simulation process decisions. Representative data are fundamental to obtain a valid and credible building model. And finally, review model results and animations to see if they appear to be reasonable. That's all, and thank you for attending the lecture.